Hello everyone. Today we are going to talk about one of the simplest yet most popular algorithms in machine learning, K-means clustering, KMC, and related to that, K-Medoids clustering. So the clustering problem, which is a branch of unsupervised learning, is basically grouping data into basically sets, clusters, whatever you might want to call, that they have similarities. And if you want to put similarities into mathematical form, we might say the distance between the data within a cluster or the group is small compared to the data between the data within the cluster and data outside the cluster. Okay, so that's the definition that you can provide for a cluster. So what's the problem we have here? We have n data points. Each one has d dimensions. So it has the feature vector for each one of these data x1 to xn has d numbers in it. We want to basically divide these n data points into k clusters where k is given a priori. We know it, somebody gave it to us, okay? Or we decided on some number, right? So how do we do that? Here, we consider a center point, an average for each cluster out of the k clusters, and we show it with mu sub k, where this small k can go anywhere between 1 to the capital K, the number of clusters. And not only we have the center point, the centroid of each cluster, we also have a binary indicator matrix, R of n and k. So you see definitely it's a matrix. It has two subscripts where the numbers in this matrix are only 0 and 1. So if you look at each row in this matrix, in each row there is only one number 1 and everything else is a 0. And where is it that it's 1? It's right at the cluster that that data belongs. So what do I mean by that? Let's say, for example, here you have 5 data points, or maybe 6 data points, x1, x2, x3, x4, x5, and x6. And let's say you have, let's say, 3 clusters. So cluster 1, cluster 2, and cluster 3. Okay, so now where does data 1, data x1 belong to which cluster? If it belongs to cluster 1, then this data here will be 1, everything else is a 0. If second row is like this, what does it mean? It means data 2 belongs to cluster 2. If third row also looks like this, means third data also belongs to cluster 2, right? So in each row there is only what? 1, 0, and 1, 1, and the rest of it are going to be 0. So this is your matrix R, correct? Where the row index shows the data and the column index shows the cluster. And now with these two, with mu and R, we are able to easily basically formulate the problem. So not only matrix A tells us which data belongs to what, the center also determines roughly where the basically the cluster is. Okay, now this method is not going to give us a standard deviation or something, so we cannot really draw some like elliptic boundary or something as you might do with the Gaussian distribution. But what you do, if I show you a picture here, if you have the R matrix, which you do, you can kind of maybe color code it or something here for visualization. And in 2D and 3D, you might still be able to visualize the cluster once the number of dimensions, that D number that we said, is beyond 3, you cannot visualize it. You can just do the calculations. Okay, so here in this case, D is 2. And so here we are using different colors. So the red data are one cluster, the blue data are another cluster, and here I have two centroids shown with these cross marks. So the centroid roughly shows where the center of each cluster is, but the boundaries, you might say they are determined by the data. So maybe this is like the boundary of this one, the boundary of the other one, maybe something like this, like a convex hull. Okay, but the boundaries are not discussed so much in K-mean clustering. All you talk about is that R matrix, which data belongs to what cluster. Okay, so going back here, now how do you determine the mu? How do you determine the R? And one reason that we need mu, you might say, well, maybe R is just enough, right? No, it's not, because as I show you, when we want to do the optimization here, the cost function we define needs a parameter mu, okay, to find what we call the intra-cluster distance or distortion. So what we do is this. We multiply the RNK by the norm of, or the distance square of, between any data point you have minus what? Minus mu of some cluster times RNK. So what does this mean? So if you look at this double summation, this is the cost function you are going to minimize the intra-cluster distance, the sum of the intra-cluster distance or distortion measure. So if I set my n equal to 1, it means the first data. So you focus on the first data, and then you change k from 1 to k. So you check the first data against all of the average points, mu1, mu2, mu3, for the example I just mentioned, and sum the distance from the first data to all of those clusters up, but you multiply by R and K. So what's going to do? So let me expand it for you for this example here. So it is going to be, as I said, let me just set n to 1 so you see what's going to happen, and then I show you summation over n. So for the moment, I'm not going to do this summation, I'm going to do the rest of it. So it's going to be what? It's going to be R11, the distance between x1 and mu1 squared, plus R12, the distance between x1 and mu2 squared, and finally R13, the distance between x1 and mu3 squared. Now, because only one of these numbers in this row, you see these numbers are data in row 1. One of them is non-zero, in this case R11. The other two terms are gonna go to 0. These guys are 0. They don't count. All you are counting is the distance between x1 and the centroid of the cluster it belongs to, mu1. Now when you do n equal 2, guess what's gonna happen? You're going to go now to row number 2, and row number 2 only has R22 in it. The other terms are 0, so the only term you will get is R22, the distance between x2 and mu2 squared. And similarly, for x3 is going to be again minus mu2 because it belongs to class 2. x4 is going to be minus mu1. x5 and x6 is going to be mu3. Right? So basically, these are what? These are the sum of the intra-cluster distances. Why? Because let's say when n is 4, what do you get when n is 4? You are going to look at the fourth row and you only have R41. And then you have x4 minus mu1 squared. So now, what's happening when you add these two data? This is sum of the, and remember, these numbers are 1. So what is it? This summation is what? Sum of the distances of all of the data in cluster 1 to the center of cluster 1. So this is basically intra-cluster distance for cluster 1. And then when you do it for the other ones, you get the other intra-cluster distances for other clusters, and you add them all together. So this is the total, I would say, the total intra-cluster distance, this J. Let me add a word total here for you to make it a little bit more reasonable. So this is the function you are trying to minimize. How? As you can see, this is a function of two variables in general. One is what? Mu. Where are the mu's? And the other things are the components of R, right? So this J, we can say this is J of mu's and the R matrix in general. So we try to find R entries and mu values that minimize the function J. Now for R, it's not so hard because clearly the J is, in terms of R, you see it's a linear function, right? It's just a linear function in terms of R, and these R's are only 0 and 1. So it's very, very obvious and simple from optimization to show that if you set the derivative of J with respect to R and K and set it equal to 0, right? Then the best decision you can make is this. R and K should be 1 if that data belongs to that cluster. Now, how do you know it belongs to a cluster? We say that data number n, you measure the distance of it to all of the mu's. To whichever one it is the lowest, that is for that cluster, you get the corresponding R value 1. For all other cluster, you get it equal to 0, right? So when I do my optimization and I start, I look at data 1. Hey, this data 1 is closer to which one of these mu's? Mu1, mu2, or mu3. If it's closer to mu1, then I set that entry 1, everything else what? 0, and continue. And remember, this optimization, you start with some choices for what? For mu's. So in the beginning, you have to select some mu's and you have to select some R values. How would you do it? And then keep updating. For mu's, you can just choose a bunch of random numbers. So you have 3 mu's, so you can go and select what? 3 random vectors, where these vectors can, in this, if I want to go with this kind of problem, 2D problem, then you say you can select 3 random vectors that belong to what? R squared, right? Select 3 two-dimensional vectors and call them mu1, mu2, mu3. What about R's? You can, in the beginning, say R and K is all what? 0, all of it. It's going to be a 0 matrix. And then, based on your data is closer to which average, you change one of the numbers in the row corresponding to that data to 1 and everything else to 0. So this is how you update R and K, very easy. How would you now basically determine the mu's? Again, here you have to take partial derivative of J with respect to mu K's and set it to 0. Now here you have a square term, so the derivative is going to be a linear term, and I leave it up to you as a practice that if you solve out of that equation for mu, the update for the mu is going to be this: summation over n, R and K xn over summation over n of R and K. So what's the meaning of that? And the meaning is what? Remember, the summation is taken over n. So if this k is 1, you are updating mu of cluster 1. It is going to be what? It's going to be summation of over n of Rn and 1 xn over summation Rn and 1. Now, summation Rn and 1, this is what? This is the nth, this is the first column, I'm sorry. This is the first column, right? You see, this is 1. This n can change, right? The row index can change, the column index is 1. So this is sum of the numbers in the first row. So that's this guy here. If I can clean it up, it's sum of the data in the first row. What's the meaning of this? It's the number of data that you think they belong to what? Cluster 1. So the meaning of this is the number of data belonging to cluster 1. What is this one? xn1, xn. So if this entry is a 1, you count that xn. If this entry is a 0, you don't count. So for this case, again, you multiply each x by the corresponding r and add them together. So in this case, it's simply what? x1 plus x4. So what is this? It's not the number of data for cluster 1, it's summation of xi's belonging to cluster 1. So you add all of the data in cluster 1 and divide it by the number of data in cluster 1. So that's clearly what? That's an average, right? When you add a bunch of data and divide by the number of data, that's an average. So that's exactly what it is. How would you set up mu k? You say now, I go to what? I go to cluster 1 and add all of the data belonging to cluster 1, x1 and x4, and divide it by the number of data, which is 2. And guess what? That is going to be my new average of cluster 1. Similarly, if I want to update cluster 2, what do you think it would be? Well, I have to add the data belonging to cluster 2. So it's going to be x2 plus x3 divided by 2. That's going to be mu2, and mu3 is going to be what? x5 plus x6 divided by 2, correct? So that's how you update the mu in each step, and you keep repeating. And you might say, well, what does this repeating do? Is that going to converge into one single operation? The answer is no, it's not. It tries to tweak mu's and r's until the value of j no longer goes down and goes to like the minimum it could. Then you say the algorithm has stopped. Now, to help you visualize this, I would show you some pictures. Here I have a lot of data and only 2 clusters. So in this problem that I'm going to show you in these pictures, the number of data for each vector is 2. The number of clusters I decided is 2. And the number of data n is way bigger than k. I don't remember it exactly, but it is probably close to, I don't know, 50 or 100 or so. I guess it's close to 100 data. And that's another important thing that you have to consider for k-means clustering. The number of data points you have should be way more than the number of clusters, at least 2 or 3 times more. I mean, if this n and k are comparable, that means each data can be a cluster of its own, which is quite meaningless. Okay? So remember, n should be quite more than k. And that's what you have in this problem. So now what would you do? So here I have a bunch of unlabeled data. No label. That's where that R matrix is equal to 0. There is no 1 in any row so that it tells me each data belonging to which cluster. And mu's, as you can see, this is mu1, this is mu2. They are just chosen random points. They do not even necessarily in the beginning need to be on the data points or one of the data points. Now we'll talk about it. It's actually a good idea to choose it to be some of the one of the data points or the average of a subset of data points. Selecting the muse in the beginning completely random like this, it just takes a few more iterations or some more computations before the algorithm converges. So complete random selection is not the best idea, but anyways, you see two random muse, all are zero, no classes yet. Now what do we do? Now we want to divide the space between these two muse. So the first thing I do, I connect these 2 points together by a line, if you do that, and then you draw a perpendicular bisector. Here, this purple line that you see is a perpendicular bisector of the line connecting the muse. Any data falling on one side of the line, you see it's labeled red, belonging to this mu. Any data on the other side belonging to blue, right? And that's exactly the definition. The data is closer to which one of these? You can easily geometrically say that because any point on the perpendicular bisector is the same distance. Once you move away from it, you are closer to one of them. Right? And then what? Now that in this step here, I have updated my R. The muse still in the same place. Now it is time to what? To update the muse. How? I say, well, if this data in this blue cluster is cluster 1, now I find the centroid of this blue data, which comes here. And then if the data in this, let me use a different color, maybe orange, is another cluster, again, I find the centroid of the red cluster, and that brings the centroid to here. So now my muse are moving. Again, in the next step, I repeat. So each iteration of this algorithm involves what? Involves one time updating R's, one time updating muse and repeating. So again, when you come here, again here you update the R's. So again, you draw the perpendicular bisector and cluster the data. Right, on one side of it is blue cluster because they are close to the blue centroid, and on the other side they are closer to the red centroid, so they are going to be color coded red. It means their R values are changing. And now that again I got some new clusters, now I will update my what? I will update my muse. So now the centroid that was here, now you bring it close to the centroid of the data, and the same thing here. And as you can see, the spread does not matter, the concentration of the data does. I mean, like if you look at the spread of this cluster is like this, but it's not in the center of the area surrounded by the data. It depends on where you have more data. Here, this area of it, you have a lot more data, so your centroid is close to the densely populated area than to the sporadic data. Right? This one is quite uniformly distributed, so it's almost in the center. Right? If I bring it like this. And then you keep going. Again, update R, update mu, update R, update mu, and now after a few iterations, you see that your muse are barely moving anymore. And the classification of your data barely moving. Look at your muse. You look at this location is almost the same as this, and this one is almost the same as this. So your muse are not moving. If you look at your perpendicular bisector, of course, it's based on the muse, it's not moving. And if you look at the classification of the data, look at that. Here, the only thing changing is this data. Look at that. It was blue. Now it is decided it is red. Anything else is not changing. So the only change you see from here to here is one R value, one R entry matrix changed. Anything else didn't. And after this, even that one is not changing. So the algorithm came down to the minimal J. And if you plot the J's versus iteration, that's this plot here on the right. This is the initial J. Some of the intra-clusters was more than 1,000 units. And as you went down, 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 now probably, I don't know, you can say probably it's about 100 units or so. While initially maybe it was like 1,100 or something. So this is the minimum, and you see at this point the area, the function becomes flat and it's not going any further down. So that's it. With two clusters, this is the location of the centroids and this is the classification of the data belonging to each cluster. Okay, so you do the update in two successive steps for the k-means clustering. Now, as I told you, it's not really the smartest idea to start the initial mu's completely off random like this, which are not even among the data set. One of the things that they suggest is either choose the mu's to be two of the data sets, or to do the better job, make them to be the average of what? The average of a random subset of data points. Okay, to start them as a random subset, them as the average of course. The average of a random subset of data points, because they are just one single point. Now, are there some issues with this method? For sure. A method this simple always comes with some disadvantages, although it's very good and easy to code, as I will show you. But one of the first things, the most important thing, is how do you decide K? Not always you know K, because sometimes the type of the problem can give you a natural selection for K. Not always you do. So sometimes you have to decide how many clusters, and that is going to have a significant effect on the number of results, right? So maybe here in this problem, if I wanted to say I wanted 3 clusters instead of 2, right? Then it wouldn't be as trivial. It might end up saying, hey, maybe this is one cluster, maybe this is one cluster, and maybe this is another cluster. Maybe. Right? So, and if you make it 4, it's even harder to imagine. So not always the data are easily separated. Sometimes there are some data that are what? That are kind of in between. Even if you look at the time that it has converged, the previous problem, you see if you draw the perpendicular bisector, there are some data close to the perpendicular bisector, and hard coding them to one cluster, rigid assignment of them to one cluster is not necessarily always the best thing. But anyways, you have to come down to what's the best value for the number of clusters. Do you just randomly select one or not? Because you know, the more clusters you choose, the better you have the chance to what? To bring down the value of J. So this is for K of 2, but if I had the chance to use K of 3, then probably I would come down to some number below that. Or if it was K of 4 or K of 5 or something. So if you plot this J versus iteration for different Ks, you see the bigger the K, the smaller the final J is going to be. And that is going to be which problem? Yes, you're right. That's the overfitting. It's like a neural network model that you're using too many neurons. It's like a curve fitting regression least squares problem or a regression problem where you are using a very high order for the polynomial. That's the same thing. Using too many clusters is overfitting. So how would you choose? This is what you do. You repeat the problem for different k values and you look at the value of j. And as I told you, the bigger the j, the bigger the k, the smaller the j becomes. But the thing is this, as I told you, if you make this, continue this at some big number k, which is exactly equal to the number of data points, this guy is going to go exactly to 0. But if you look at this curve, there is some region that there was some significant drop, and there is another region that there is not a significant drop. So if you can find a point that you can approximate your curve with kind of like an elbow behavior, like this, then this elbow point is the k corresponding to this elbow point is going to be your k optimum. Okay? Now, in many problems, it might be a good idea to try this method because you will see a significant breakpoint like that. Not in every single problem you will see a curve like this. In some problems, it might be something very gradual like this. Then finding a breakpoint is not necessarily easy. There are other methods in the literature to decide how to find the best k out of all this. They might look at the percentage drop in this and say maybe at 90% drop or 80% drop, correct? So they might give you a percentage. Hey, at 90% drop, I would say that's a corner point. That's like what you do in strain curves in solid mechanics, right? When there is no clear yielding point in the stress strain problems. Or you might instead use the logarithm of these curves, right? That's what you do in controls. When you do Bode diagrams, instead of the smooth curves, you might look at their what? Their approximate logarithms or tangent to the curves. You might look at the tangent to the curves and look at the breakpoint here. That's what you do in controls when you want to find a corner point. You might do that. There are other methods like the silhouette and so on. Hopefully I'm writing it correctly. Right? So there are so many methods in the literature telling you if there is no clear elbow point, how you should do it, or they might just completely replace, like this one, replace this elbow method with a different method to come up with the best value of k. So I don't want to discuss every single one in this video because the goal of this video is to introduce you to this topic, not to basically study everything in the literature relevant to this topic. But k-means is the base. There are so many improved versions of k-mean in the literature, and I will leave them to you to study. So that's one, deciding the k. One other problem you might see with k-means is we always assume that the j function drops to the global minimum. Not necessarily. Sometimes this is an optimization problem, and this cost function, if you can plot it somehow for a simple problem, you see it has lots of ups and downs. It has local minimas, okay, it has plateaus, it has so many things, and for your optimizer to go with this gradient descent algorithms and go to the minimum point, sometimes they might be what? Trapped in a local minima or come to a stationary point on a plateau. So not always you start from some initial guess. Now you might say, where is your initial guess coming from? Your initial guess comes from the initial selection of the mu's. That will tell you where you are starting. That's your start point. Okay, not always you are able to go all the way down, roll to the global minimum. So what should you do? one of the things you can do is, as with many other optimization algorithms, you start the method with several different guesses. So start it with several different sets of mu's and see if any of them reaches a number below the others. Then you might say, well, that might be a better choice for minimum than the rest of them. Okay, so that's another thing. Not always the problems are simple and the convergence is guaranteed. And that's the problem with the steepest descent method. Finally, or not finally, one other thing I have to mention is the type of the feature and the shape of the clusters. Not always the data that you get in the data you have in your feature vector necessarily allow for a simple cross-clustering problem. Because if you remember here, you are separating two clusters and there is a perpendicular bisector. Now, if data come like this, so the data you have for each data point is x and y of it. And when you draw the scatter plot without first clustering the data, you will see this kind of donut shape. There are two rings or two circles. Now, clustering here with the K-mean clustering with K of 2 is not necessarily possible, because what it does, it kind of might end up with the mu's here and then saying, hey, this is the perpendicular bisector, and data on one side of it is this, and data on the other side is this, while this is clearly not a good clustering. The better clustering would have been, you say this is one cluster, and then this guy here in the outer ring is another cluster, right? So this is one cluster here, and this data in black is another cluster. This is the proper clustering, but definitely with the selection of x and y belonging to each data point, that's definitely not a good choice. Now, maybe I don't want to call it x because I have another x, so maybe I call it z data. That's okay. Right? So in many cases, you need to change your feature vector from this. Maybe you change it to r and theta, radial distance and angular. And then the angular is not real, the angle is not of any matter, but r is. So here clearly r less than one number, which is r1, is going to be cluster 1, and then r, right, let's say bigger than some r2 and less than r3, for example. That can be cluster number 2, where this is r2 and this guy is r3. Okay, so changing the feature vectors in many problems can give us a lot better clusters than just trying to stick to the same feature vectors and just playing with the number of clusters. Many times it's better to completely change the feature vectors. Now, one other point I have to mention is the K-mean clustering is not necessarily suitable for clustering data series. Why? Because the data component will be hidden and will be lost and will not be really used. So if I have some set of data here, some portion of this data I have over here is captured in some time t1 and the other portion of it t2, the other portion t3, definitely this simple graph is not going to show any indication of t1, t2, t3. All it shows is x and y. And so t is going to be hidden and it's going to be lost and it's not going to play any role in my clustering. So in general, it's better to apply to problems with static nature, not problems that the time is an important factor that you really have to add to here. Okay, unless again you add the third vector here, call it t, maybe that can help. But in general, we don't really necessarily use K-mean clustering for time series and analysis of time series and prediction. We use other models in machine learning. Now, here we go to applications of this K-mean clustering in real life. Okay, so now I can cluster the data into a bunch of groups. So what? Where would I use it in real life? Let's take a look at that. The first application could be image segmentation, which is to divide an image, partition an image into groups that they have similar appearance, okay, or homogeneous visual appearance. So, for example, if you have an image, you might wonder, what is it that goes into each one of those X's, right? What are the features? Well, one of the most common things is color, and color could be different versions of a color space. And the simplest one that I mentioned under my playlist, Computer Vision Image Processing, are red, green, and blue values. Now you might instead use HSV color space or LA star B star color space or any other color space, right? And what it does, as with these images, depending on how many clusters you use, it kind of partitions the image into those different regions. Now, it doesn't necessarily mean that those regions are necessarily the same object, right? So, for example, here you say what? You say 3 clusters. Here it considers the hair of the boy and the neck area, and then under the arm, and then the background of the body of this whatever person it is. It makes all of them brown, plus probably the hair of the guy and a portion of this hole here, right? And then it does the rest of it, some areas blue and some areas yellow. So although the yellow area is kind of similar, but you see the face of the boy is a separate region really from the plastic yellow opening, right? So that's one of the reasons this simple segmentation with RGB value only is not the best way. You also might want to consider spatial proximity, right? X and Y. So if you add X and Y in this picture, or if it's pixel coordinates, U and V, right? The pixel coordinates, that would be a lot better in the 5 space, in the 5-dimensional space. If you do clustering, that would probably make it a lot more meaningful. But anyways, you see the problem of segmentation here. Segmentation is still an open problem. There is no perfect solution to segmentation that has been brought up anywhere in computer vision literature. They are even with U and V, you see, it's close to impossible to make it perfect, although it makes it a lot better than RGB, or some people use LA star B star and U and V, right? And you can get better results, but still that's an open area. So that's one. The other one is lossy data compression, where instead of storing the original data, all of these X's, right? Let's say you have this XN, this N goes from, let's say, 1 to 1,000 data points. If you cluster this data around maybe, let's say, 20 clusters, then all you need to store is literally mu k. You have 20 mu k's, and then you have one R matrix. Okay, you need one R matrix, and the dimension of this R matrix in this case is going to be what? Is R of N and K, where N is 1,000 and K is 20. Plus this R matrix is all zeros and ones. So literally what you need to store, depending on the dimension of these X's, instead of 1,000 data, each one of them, and let's say X is like this top case here, 5 by 1. So instead of storing 1,000 data, each one of them containing 5 numbers, which is 5,000 numbers, right? And these numbers could be anything. All you need to store is now 20 times 5, which is 100 real data. And then, although this guy is going to be a huge thing, 20,000 numbers, but they're all zeros and ones, and you might even save it as because each row only has 1, 1, so you can save it as a sparse matrix. Okay, so at the end of the day, although this R matrix might look like big, but it's not going to take a ton of memory, especially because for each location, for each entry in it, you only need 1 bit. So this is going to be like 20,000 bits because each entry is a 0 or a 1. While here you have what? You have 5,000 values, and if these values are uint8, or maybe more, then each one is going to be 8 bits. Okay, here you have 100 times 8. So the total of this is going to be 20,800 bits, while the original data is going to be 40,000 bits. So you see, you get a compression of about 50% if all you store are the mu's and what? The r's. And so if they say at each point you want to show the xn, instead of xn, you show what? The associated mu for that xn. How do you know which mu that xn is associated with? From the R matrix. So instead of showing all the values in x, you only show 20 values of mu, and this is what we call quantization. Right? And this is a lossy form of compression, data compression, that you can do with K-means clustering. What else? So before I move to the next topic, instead of all of these blue data, anytime you want to show the blue data, you only show them with this cross point, and all of the red data, you show it with what? With this cross point. Now, what's the problem here? The problem is this with the K-means. In K-means, the mu's are not necessarily one of the actual data points, okay? So none of these two black cross points are any of the blue or red points in general. Accidentally, they might fall on them, but in general, they are not necessarily any of those points. And that's one of the problems, that the mu's that you store in K-means clustering, if they are just some points not representing any of the real original data, they might not be a good representation of the original data. So that's one of the reasons that instead of K-means clustering, we might go to the alternative approach for clustering is called K-Medoids. What is Medoids? Medoid or exemplar, which is we're going to see in a second, is basically a point in your data among your actual data point. One of the point in your data point that has the minimal amount of what we call dissimilarity to the other points in the cluster. So this time the Medoid might look something like the average, but first of all, it's one of the actual data points. If I can zoom in, you see it's definitely one of the actual data points, and the dissimilarity between this point and the rest of the points on the cluster is minimum. Now you might say, what do you mean by dissimilarity? Well, anything that can measure the difference. One of them could be the same as what? The Euclidean distance that we used in K-means. That is a measure of what? Dissimilarity or distance. But the good thing with K-Medoids is it allows you really in its original form to choose other forms of distance, not just Euclidean distance. And then you might come and say, well, what's so wrong with this Euclidean distance? That looks like a nice quadratic function. You can easily take derivative of with respect to mu or something. That's right. In terms of derivative and optimization, it is an easy function. The problem is it is very susceptible, it is very sensitive to outliers. Okay, if you have outliers in the data, And if you use Euclidean distance, it makes your algorithm non-robust to the outliers. And you might say, like, what? What do you mean? Here, take a look. Here I have all of this data that you can see. I have all of this data, right? And here, instead of the data that I have originally, I added a few outliers, one category here and a little bit here. And look at what the K-means did. I said, bring this whole data into two categories, two clusters. Tell me where the averages are and which data belong to what clusters. All I did, in addition to this nice two clusters that I have in the ellipse, I added like 5 data points here and some 4 data points here, right? 9 outliers is all I added to see whether the method still gives me something reasonable like it did here, right? It's the same as this picture. The data in the bottom picture is exactly the same as this top picture. If you look at them side by side, they are kind of very similar, except here I added some data here and some data here. And look at what the K-means did with the Euclidean distance. It says, guess what? I think all of this data are one cluster, and this portion is one cluster. So it made a group of outliers a cluster of their own, and the rest of the data with the other group of outliers another cluster of their own, which is clearly what? Falling to the trap of outliers. What it should have said is, hey, like what this one you can see here on the right side, this is the K-Medoids algorithm with K of 2. It says, hey, I still think this is one cluster, this is one cluster. And these two groups, one group belongs to this cluster, one group belongs to this cluster, and they are not really clusters of their own. First of all, we didn't allow it because we said K is equal to 2. And it definitely gave you much better representations with mu's, right? This time they are not mu's anymore, they are medoids. So this is one medoid or one representative, this is another one, right? You see clearly how much better these medoids represent the data compared to these two black crosses. So the K-means with the Euclidean distance is not robust with the outliers. So what does K-Medoid do that makes it so nice? It allows you to use other distance measures, not just Euclidean. And you might say, like what? Well, one of them could be the Manhattan distance or the city block, or the taxi cab, you might call it distance. I mentioned this in one of my prerequisite videos on machine learning language, the Manhattan or city block distance. This is one of the ways you can measure distance. You can also measure Chebyshev, right, or L infinity. This is L1 norm. You can also use what? You can also use L infinity norm. You can also use the Matlab distance. You can also use the cosine angle, and there are so many other distances. I'll show you all options you have in Matlab when you want to run any of these two, any way of the K-Medoids. It allows you to choose a lot of different options for the function. Okay, so the K-Medoids has two advantages. One, it allows you to use other functions, which makes the method more robust to outliers. Two, the medoids or the exemplar data or the kind of centroid, they are not real centroid, they are generalized centroid medoids that you choose, they are actual data points. They are not just somewhere in between them. They are actual data points. These are two big advantages of the K-Medoids over what? Over the K-means clustering. So now you might wonder, okay, so how do you describe the K-Medoids algorithm? So first of all, the cost function that you use is very similar to last time. Still, it's what? It's a distortion function. Still, the association matrix Rnk is multiplied, but instead of this function being the norm 2 of xn minus mu k, this is what? This is now any function that can provide a dissimilarity. Okay, any function. We say nu of xn and mu k. And mu here, by the way, does not necessarily mean what? Necessarily mean the average. It's not the average. It is called the medoid. Okay, so here, this guy is called medoid of the cluster. Right? So, one of the very famous and basic ways of performing the K-Medoids is the PAM method. PAM is partitioning around medoids, or PAM. This is one of the most famous or well-known methods for performing K-Medoids. What does it say? It says first initialize, select K and N. Right? Of course you can. You select the number of clusters and you have n number of data points. So first thing, just like K means, you have to select the number of clusters. You have to select the number of, let me use capital K here. You have to select the number of clusters, okay? You have to do that. Then associate each data point to the closest medoid and n data points as medoid. So let me emphasize on this part before I go to part 2. It says what? Look at that. It says select n data points as the medoids. Actually, if you have k clusters, you have to also select k data points as the medoids. You cannot select n because you have k clusters and k medoids. So out of all of these xn's, where n goes from 1 to n, and n is a big number, much bigger than k, randomly select k of these numbers and assign them to the mu k's. So mu k's are not average of anything, they are just random selection of k numbers out of n numbers. Select k and choose k random data points as the medoid. Then it says associate each data point to the closest medoid. So now you go over each one of these x's, let's say for example x1, and see this x1 is closest to which one of the mu's. So between x1 and mu1, you calculate the nu function, then you do nu of x1 and mu2, and all the way down to nu of x1 and mu n, or mu k, I'm sorry. And then see which one of these nu's is the minimal. Let's say, for example, it's this guy. If that's the case, then the first row of your R matrix is going to be what? The second element is a 1, everything else is a 0. Right? And then you perform it for x2 and all the mu's, x3 and so on. So instead of the Euclidean function, use the dissimilarity function that you chose. That's step number what? 2. Now, how do you do the loop? Instead of those 2 successive steps that we mentioned, now you still have 2 steps, but a little bit different this time. It says for each medoid m, if you call it m, instead of m, you might call it mu k. And for each non-medoid data O, which is like xn, what would you do? Consider swapping m and o. So what happens if instead of what? Let's say you consider what? You went for x1 and mu1. It says, can I swap? Bring mu1, replace x1 with it, and then x1 becomes mu1. And then do it with x1 and mu2, x1 and mu3. So it needs a lot of computation in these steps because you have k mu's and you have what? You have n data points. And if you want each pair of these, you have n times combination you have to calculate. And then what? When you do all of those, you calculate for each one of those n by k combinations the new cost function. See if you, for example, exchange or swap x1 and mu1, is that going to bring the smallest j that you had in step number 1 and 2, does it bring it down to something smaller? If it does, it says if, as you can see, it says if the cost change is the current best, it doesn't say you do the swap, it says remember it. So remember that, hey, when I was looking at all of those n by k combinations, when I swapped x1 and mu1, it could make j decrease. So I'm not going to do it immediately until what? Until I look at all of those different changes in j, because each one of them will give you a new j tilde value. And then see if any of these is better than your j minimum that you had in the previous step. If none of them does, so your previous set of x's and mu's were the best, then the algorithm what? Terminates. If no, some of these swaps led to smaller means that j mean, then which one would you do? The one that was the lowest. Let's say the second one or the 10th one or the 20th one, this was the min of the mins, then I will do that, whatever swap that caused such a thing. So when I'm looking at the swaps, I'm not going to do a new swap. If I find any new swap that is less than my current best, I'm not going to do it immediately. I wait until I see all of them. When I see the best one, then I pick the best one. If there is no best one, if there is, by best one, if there is nothing better than the previous, then I would terminate. If there is something, I choose the best one and do it. So as you can see, it needs a lot of computation. Because in each step of the iteration, I'm doing a ton of potential swaps. Potential. I will do one of them, definitely. But I have to look at lots of combinations, do lots of calculations of this similarity function, and then what? In each step, all I'm doing is one single swap. Guess how many of these swaps you have to do before you bring j to the minimum that it can possibly have, to the lowest value you can have. That's why the PAM method on its own, in its simple form, is a very costly operation, much, much costlier than the K-means. So that's why there are so many modified version of PAM that are in the literature, which makes it a lot more doable than the basic PAM. And again, since my goal is not to go over each and every one of those variations and so on, I would allow you to go and deep into different versions of PAM, fast PAM, and so on. Okay, if I have to make another video on this topic alone, K-Medoids, separately, I can talk about those different versions and all of the details. But I would rather just mention them and let you do the rest of the study. So now, if I want to recapitulate the good things about K-Medoid, 1, the Medoids are actual data points, not just centroids, which are not on the top of the data points. 2, because I can use any dissimilarity function, not just the Euclidean distance. I can choose the ones that make my algorithm more robust to noise and outliers. Okay? These are the two big advantages of this algorithm. And in here, the cluster is really a what? It is the medoid of a cluster. The cluster is still the same definition. The set of points for which the intra-cluster dissimilarity is much less than inter-cluster dissimilarity. And the medoid is the point inside the cluster whose average dissimilarity to all other points is the minimum that it could be. Okay? So that is the K-Medoids algorithm. And now if I want to show you some Matlab code, because I know you probably are waiting for it, here I have got a good portion of this code from a Matlab example. So here I generate some random data, and then I plot the random data for you, which is basically 200 data points. So here we go, right? 100 data point here, 100 here, and I wrote the random function so there is some visible gap between the two clusters, right? I make this, and now what? First, I use the Matlab built-in k-means function. This is the command in Matlab, k-means. You pass to it the cluster, the data, all of the data in the cluster, and the number of clusters. And it can give you what? The IDX. What is this IDX? This is exactly your R matrix, the association matrix. It gives you C, which is all of the mu's or the centroids, and it gives you some D. What is sum D? Sum D is this J function, but instead of being taken over all clusters, it's only taken over one cluster. So basically, instead of being double summation, it's only summation over n. There is no summation over k. It gives you actually one J number for each cluster. So in sum D, if you add all the numbers in sum D, to put it simple, if you add all the numbers in that sum D variable, that is going to be this J function. Okay? And here, I use the built-in function, and I apply k-means and then color code the data. So now you can see these are the centroids, and these data are one cluster. These data in blue are another cluster, doing its job very fine. In the next step, I wrote my own k-means, which is probably much simpler than Matlab k-means, because I did not do a ton of checks and a ton of code optimization. I wrote it very simple, and I show you. And by the way, I will share both of these M files under the video description for you to take a look. In order to run the first command, the first M file, you need to have statistics and machine learning toolbox. So Matlab has this amazing toolbox. Okay, it's called the statistics and machine learning toolbox of Matlab. It has a ton of amazing machine learning functions, from k-means clustering to principal component analysis to k-nearest neighbor to mixture of Gaussian and so on and so forth. It has them all. But of course, not everybody has this toolbox because you have to pay some money for it. So for those people, I wrote my own k-means algorithm, which is very simple. And if you want to run this one does not need any toolbox. This is just done based on some simple vector operations. So the only reason I did it is, first of all, for those of you who don't have the toolbox. Second of all, I wanted to show you that the result of my code and the result of Matlab code are similar. So here I run my code, and then I guess I closed the previous one, so let me run the previous one. And if you put them side by side, they should be identical. Look at them. Right? This is my k-means, this is Matlab k-means. And clearly you see the associations and the centroids are on the top of each other in both pictures. So my code does work. Okay, and then here I have the K-Medoids. So here I run the K-Medoids command, which is also in Matlab toolbox. You pass to it the data, you pass to it the number of clusters, and it allows you to choose the distance. You provide the name of the type of distance that you want. What kind of function, what kind of dissimilarity measure do you want? Here I set city block. By the way, I need to emphasize that In Matlab built-in function, for this one, you can also provide a what? A function. This is a little bit different than the original definition of k-means, because the original k-means is defined based on what? Based on the Euclidean distance. So the built-in k-means command of Matlab is not the original k-means, it's like the improved version of k-means. Okay, you can change this function, and so in that way it takes away one big advantage of K-Medoid over K-means, which was robustness to noise. Now for this one, if I want, I can also take this option, this one, for the K-means of Matlab and say what here? I add it like this. I can do that if I want. Then the only advantage of K-Medoids in Matlab over K-means is K-Medoid centroids are actual data points, K-means is not. That's the only thing, because now I can provide, and let me show you that. So if you say K-means in Matlab and go to help, you can see, you see here, x, k, it gives you idx, c, sum d, and so on, and it allows you to choose a function. Let me go down and show you that actually here. It allows you to choose a squared Euclidean distance, which is the default, cosine function, correlation, CT block, Hamming. So it has 5 options. Okay, that's the advantage of Matlab built-in function. It's a little bit more powerful than the simple. K-Medoid has more options. K-Medoid's function in Matlab, if you look at it, it has a similar syntax. It can give you the association matrix, the Medoids, the summations, the individual j's. And if you look at the functions here, it has a bigger list of functions. Euclidean, square Euclidean, standardized, CT block, Minkowski distance, which is a p-norm really, Chebyshev, Mahalabanes, cosine correlation, Spearman, Hamming, Jacquard, and you can even provide your own dissimilarity function. So that's the power. It allows you to define your own dissimilarity function and use that one. Okay, so it gives you that powerful of a thing. And here, you can also say how this method is going to do it. The default of it is the PAM method, which I told you, the PAM. It is heavy in terms of computation. There is another version of K-Medoids called small. There is one called Clara, which is the abbreviation for clustering large applications. And then there is a large. Okay, so there are 4 different versions of implementing this algorithm. Other than choosing functions, it has different versions of that. Okay, so maybe if you have a lot of data points, you don't go with PAM, you go with Clara, because this can handle large amounts of data. Okay, so this is the K-Medoids default in Matlab, and if you run this guy, here I did the same thing on the same data, and you clearly see that the association of that is similar to the K-means. If you look at the color data, it's no different than the data of K-means. What's the difference? The difference are the average and Medoids. Look, see, it's the same thing. But now if you look here, if I zoom, that average does not fall on any of the actual data. You see? No red point is on that. But if you look at the Medoid, they are. Look at that. You clearly see this Medoid is exactly centered at that data, and the other Medoid is on another blue point here. So that's the big difference you can see here. And then here I created the elbow chart, which is here. I created this function and show you that For this type of data that I have, if I go with 2 clusters, that is going to be the point after which the decrease in J is not significant. Before that, it is big time. So I want to show you, create this elbow function. So I change the value of K. I rerun my K-means. Each time I get J out of all of those sum Ds. And then I will basically create this elbow plot. So you see here, I go from K of 1 to 10. I get all of those sum Ds. I add them up to get J. I store it and then I plot it. And if you do so, look, you see, you jump from 1400 from K of 1 to less than 200 K of 2. But then from K of 2 to K of 3, you go from 73 to what? To 126. So the reduction here is only what? About like less than 50 points, while here the reduction is, as you can see, about 1200 points. So you clearly see that I have what? I have the kind of flatness after this point K of 2, and that's why I can consider K of 2 a good optimal point here. I can see a clear elbow point in the graph. So, and then I have the code for robustness of the noise, which will generate this two data for you, these two graphs, I'm sorry, right? So it can generate these guys, which show you the Medoid can tolerate some noise and outliers, while the K-mean might or might not. Now, it doesn't mean every time you run the K-mean, you are going to get what? You are going to get this graph. No, one time you might get it and it does the correct thing, like this one, consider that and this to be one cluster. It all depends on your data. It all depends on your data, because each time you run my code, it generates some new set of data. They are random data. Okay, and even the noise that it will create here for you, it adds 4 and then 5, 9 total outliers. There are going to be some new locations too. So it doesn't mean if you run this code each time you will get the same graph that I did over here, but you clearly get the idea that it's not always working with outliers, while the K-Medoid every single time delivers with a reasonable amount of outliers. Okay, and finally, this is my own code. So you see here, it's a function. I get x and k. I return idx, R matrix, the muse, and some the how. First, I get the number of data points. Make sure the number of data points is no less than twice as much as k. In other words, I at least have 2 data points per cluster. If I don't have 2 data points per cluster, I'm not going to do it. I'm going to throw an error at you and say, hey, you don't have enough data. You might bump up this number and say, hey, if you don't have less than 5 times or 10 times, don't do it. But here, I'm trying to take it easy on you and say, as long as you have 2 clusters, you give me 4 data points, right? Again, you can bump up these numbers at your own will. The threshold for no change in the muse is 1/100. Okay, and my numbers are quite big here. What you can do, you can normalize your data if you want to make it better. And then this has more meaning, this number, because this 1/100 could be a small number as long as the magnitude of your x's are big numbers, more than 1 maybe. But when these numbers in x are 0.1 or 0.01, then that's a big threshold. So it's a good idea if you first normalize your x's. So divide all of the x's by the maximum x that you have along each entry in the x's, normalize them, and then look at this threshold here. I haven't done it. As I said, this is not the optimal code. It's just for demonstration. Then here I randomly assign k data points out of all data points to my muse. So I'm not starting muse randomly. I'm starting muse randomly, but what? From the original data point. K random points out of the data points. I allocate my R matrix with a bunch of zeros. I start initial mu as mu0. This mu0 is something I later compare it against the mu to see if the change in mu is significant or not, and I should terminate the loop. I have a variable that if it's 1, the loop will go on. If it's 0, the while loop, the update loop will stop. Then in the update loop, I have step number 2 and step number 1 and step number 2. Step number 1, I assign the R values. How? I subtract each X from what? From all of the mu's. This mu is a matrix including all of your mu's. I subtract, let's say, data number 1 from all of the mu's. I use a 2 norm, and I use the subtraction over what? Over the rows. That's what this command wec norm does. Because if I didn't want to do so, what would happen? Let me show you here. So here, when I say that mu is like this. Mu1, it's a vector of its own. Mu2 all the way to mu k. The dimension of these mu's is each one a what? A 1 by d. Then I take data, let's say x1, which is also 1 by d, and I subtract this x1 from each and every one of these mu's. Then the result of that subtraction, mu minus xi, or xi minus mu, is going to be a matrix. Now, when you apply the command norm to a matrix, it will give you a single number. I don't want a single number. I want to give me norm of row 1, norm of row 2, all the way to norm of row n. The norm command is not going to do that. It's not going to get a matrix and returns a bunch of numbers like norm 1, norm 2, right? It's not going to do that for you. The command wec norm does. If you pass to it the wec norm, this data, and then say wec norm of this data, and 2 and 2, the first 2 is the p norm. When you say 2 means 2 norm, L2, which is the Euclidean distance. The second one, 2, means do the norm over what? Over rows, because it can also do it over columns. If instead of this 2 you say 1, it does the norm over column, and then it gives you a row vector, like norm 1, norm 2 all the way. I want it over the rows so I can see the distance between that x and all the mu's. And then decide this x1 is closer to which one. So then I run a min command on this vector, and wherever the min is, that corresponds to a 1 in the R matrix. Everything else corresponds to a 0. And that's exactly what I'm doing here. So first I update the R. Again, I need to use the command built-in function wec norm. And then I update the mu's. And for the mu, I do that summation that you saw in, where is it? Should be here. This guy. Which I add all of the x's belonging to one row and one column, and then divide it by all of the ones in that column of the R matrix. So here I'm exactly doing it. You see the R, right? That column of R is dot producted, really, pixel-wise producted with x. You take a summation, right, over columns, divided by the summation of that column in R matrix. That's that new mu. So you update mu, you update R, and keep going. How far do you go? As long as the change in the mu, which is the norm of mu minus mu naught, remember you already saved the mu naught in the beginning. Now that you get some new mu, you compare, you look at the norm of that, and as long as this change in the mu, the norm of it is less than the threshold, what? If it's less than the threshold, means it's not moving anymore, so you change flag to 0 so the loop stops. If it's bigger than the threshold, you still should go. You don't change the flag, flag stays 1, the loop continues. And if you stop, then you're good to go. If you don't stop, not only you don't change the flag, this new mu that you get, now you store it as the old mu also. Because next time you come in the loop, the mu changes. So you store the current value of mu as mu naught. So the next value of mu, you can subtract from the current value of mu over here. So you have to store the current as the old mu. And ultimately, your mu's are going to be your C. And then wherever in R matrix, in each row of that, you find a 1, because find only finds the ones in a row or a vector or a matrix. So you go over each row. Wherever the number is 1, you find the location of that using find command. That is going to be IDX. So this IDX here is very similar to the R, but it's not a matrix. It's only a vector. So if I said IDX is the same as R, that's my mistake. Sorry for that. IDX is similar to R, not identical. RDX is a vectorized version of R. It's like a collapsed version of R. So if, let's say here, this is my R matrix, what is going to be IDX? Well, IDX is going to be like this. Hey, the first data is cluster 1. The second data is cluster 2. The third data cluster 1. Then I have 1. Then I have cluster 3 and 3. So the number of the cluster each data is associated with, that's IDX. That's not a bunch of ones and zeros. And that's why I use the command find to find me the index, the location, the cluster number, and save it as IDX. And then, of course, I use my summation of deviations from each mu to all the data belonging to that cluster, which I got it by pixel-wise producting of all of my x's with the ith column of R, subtracting from that mu, and then taking some of the summations over the number of over the rows. Okay, so this one gives you the exact same thing that the k-means command in Matlab does. So hopefully all was useful to you. It was a long lecture. I tried to cover as much as I can in about 1 hour 27 minutes for these two very important, simple, and well-known, commonly used algorithms in machine learning. Thank you so much. We'll see you in the next lecture.